Now we're going to take 1 minute to talk about polytropic processes. So a polytropic process is an isentropic process for an ideal gas where we're expanding or compressing an ideal gas. So it's delta S equal to 0. And then what we see for this polytropic process is that PV to the power n, which is constant, is constant. So as an example, the easiest case is when n equals 1, what we have is P1V1 equals P2V2. And so this is for an isothermal expansion or compression of an ideal gas. This is what we have. So for n equals 1, it's isothermal. All right, another case that we have is in fact what we are dealing with, and if n equals gamma, gamma is the ratio of specific heats. So Cp over Cv is gamma, it's the ratio of specific heats, and if n equals gamma, we have P1 V1 to the gamma equals P2 V2 to the gamma. This is for an adiabatic process. So if n equals 1, we're isothermal. If n equals gamma, we're adiabatic. And remember, that was one of the not boundary conditions, but that was one of the assumptions that we made when we were setting up this problem. We assumed that Q was 0 when we were applying the macroscopic energy balance. So using this, we can now write P1 and V1 as a ratio. So we can write this, we have P2 over P1 so we're going to take this, say P2 over P1 equals, so this will be V1 over V2. These are both raised to the gamma power, so raised to gamma. We can use the ideal gas and rewrite this as T2 over T1. We're using the ideal gas law, so just replacing with the ideal gas law. T2 over T1 equal to V, this is V1 over V2, and if you work this out algebraically, it's going to end up being 1 minus gamma.